So hey guys, welcome back to the new video of binary search algorithm. Now why binary search algorithm when we have linear search? Because linear search actually takes a time complexity that is much more bigger than the binary search. And how does binary search actually helps in reducing the time complexity? So all these answers you will get at the end of this video. And I make sure that the video is really very simple to you and you are able to understand the code, and that too a very short code that I will help you to understand. Okay, so what happens actually in linear search? You actually search each and every element and go till the last and until you find the element. In that case, the time complexity is around order of n. So we will try to reduce this time complexity with a intuition that is actually involved in the binary search algorithm. So let's divide this video in two major parts. The first part is the intuition part, where we will understand the actual logic, and the second part is the coding part, where we will actually code live in order to understand and get the result. Let's start with it. So firstly, I'm going to open a whiteboard. Okay, I hope this is visible to you. Cool. Okay, so let's start with it. So just suppose you have a particular array. Okay, and here we have to remember that in binary search, all the elements have to be sorted in order to implement this binary search algorithm. So it is starting with 0, 1, 2, 3, sorry, 0, 1, 2, 3, 4, 5, 4, and 5. Okay. Elements here are as 2, 8, 10, 12, 13, and 19. Okay. Now just suppose the element that we have to find is x, that is 13. Okay. So what we'll do, we will mark L here, that as the lower element, and H as higher element. Okay. So what are L and H? L is 0 and H is 5. So the major intuition behind this is finding a middle element. Okay. Let us write here. Finding a middle element in the array, and then a lower element, and then the higher element. In case the middle index element is equal to x, then that is the particular index, that is m, we have to return. In case, if it is greater than, if in case arr of, suppose there is arr of m, that is middle element, if in this x is suppose greater than this element, then what happens? That means it lies between somewhere m to h. So we will change this l to, we will change this l to here somewhere, just above m. So what will we make it as? L plus 1. Okay, and we will keep on repeating this process until we find it. But if in case it is arr of m is greater than x, that means x is less than arr of m, then that means it lies here somewhere. So what we'll do, we will shift this h to somewhere here, that is here. Okay, this is actually m plus 1, it will be there. L will come here somewhere and will be m plus 1, because just increment of m is what? M plus 1. And what will happen to this h? It will come here to 1 less than m. So it will happen what? M minus 1. Okay. So let us understand the actual intuition finally. Suppose what is the middle element here? It will be L plus h minus L by 2. So what is L? 0. What is h? 5 minus 0 by 2. That is 2. So we got to know that 2 is the middle element at first. So let us write this. Let us remove this particular logical part. With a clear explanation of the example, you will be able to understand it properly. Okay. If you're not able to understand, you can just ask me in the comment. So what is the middle element we found? Middle index element, m is equal to 2, somewhere here. What is this? 10. Okay. Now, at first point, what is L? L is equal to 0. H is equal to 5. and m is equal to 2. So let us check if x, what is x is what, 13, is equal to ARR of m. ARR of m is what, 10. It is false. So what is actually it is that what it is actually 13 is greater than 10. That means x lies somewhere here, isn't it? So what we will make, we will call the binary search function recursively, and we will put ARR here, comma, what we will put, L has to be moved to here, isn't it? So we will put m plus 1, comma, h, comma, x. Now, why we are putting in this fashion? We are assuming that our initial function is as binary search ARR, comma, L, comma, H, comma, X. Okay, where our values at the starting are 0, 5, 13. Okay, now this will be called again. Now here what it will become? What L will become? L will become m plus 1. So L will become m is what, 2 above. It will become 3. H will be what, 5 itself, and X will be 13. Now let us see. 13 is equal to m. What is m here? Let us find that. So 3 plus h minus L, 5 minus 3 is 2 by 2. That means 4. So ARR of 4 is what actually? It is 13 itself. So that is true. So this true will be returned to this particular function above with the, or if we are returning the index, then we can return the index itself. So what is the index here? 13 index is 4. So we will return 4 here. So this will get 4, and then finally 4 will return to the answer part. Okay, so this is the actual intuition behind this. So what we are checking actually, let us write the sample code here. We are checking that if ARR of x is ARR of m is equal to x, then return m. That is the result. If x is greater than ARR of m, then do a binary search again, return a binary search again and fill the value as ARR, comma, since it is greater than m, what we'll do, we will write m plus 1, comma, h, comma, x. Else what we will return? Binary search ARR, comma, here L will be same, it will become m minus 1, comma, x. And if everything is wrong, we are not able to fetch any value, we are not able to get the value itself, then at last we'll return -1. So this will help us to get the actual index. Okay, now let's try to write the actual code. So as you can see here, you have been given a sorted array, integer array of size n, element x. Write a function to search this element in the given input array with binary search. Return the index of the element in the input array list. If the element is not present in the array list, then return -1. Okay, so let us write that. Firstly, we have to find L. Int L will be what? 0. Int H will be what? ARR dot length -1. And then we will just find the create a new function, and we will let's give the name of that function as binary search result, and put the value as ARR, comma, L, comma, H, comma, X. Okay, now let's create that function, public static int, and then this particular function name. Let us write the receiving variable names, int ARR, comma, int L, comma, int H, comma, int X. Okay, now we have to give a first, at first point we have to give a check condition that until when we our particular like iteration should work until when our recursive approach should work. So the first like checkpoint which we have to give is that just suppose L is at the first point and H is at the end point. There might be a place where L and H collide each other, and that would be the index where the element is found. But in case if it is, we have to just see a case where it has becomes false. So if in case it is not found, so what will become? L and H will move away from each other. So we have to make a function where until we have to make a recursive function until H is greater than or equal to L. Okay. So that will be our check condition until H is greater than or equal to L. Till that point we will check. Okay. So let us find the middle element, that will be L plus H minus L by 2. Okay. Now let's check with the first condition. If ARR of M is equal to X, return M. Else if ARR of M is less than X, or we can say X is greater than ARR of M, then what we have to do, we have to call this function for the next recursive call. We have to actually return the value also because we are finding here the values every time. So int ARR will go, since X is greater than ARR of M, that means L has to shift. So L has to shift to M plus 1. H will be same. X will be same. In case else apart from it, what will happen? That means ARR of M is less than X. ARR of M is greater than X. Then what will happen? H will shift. So L will be same actually, and H will be M minus 1. Okay. In case all the conditions are false, at last no recursive approach works, then we will return minus 1. Now let's run and check this. So at first attempt itself, we are able to find the solution. And but that doesn't mean that every time whenever you write the code you are able to find the solution. Sometimes you may miss something, but you have to be very keen, try to reprocess that code, take a pen and paper, try to rework on that with a test case and work with the solution. You will get that where the particular point you are missing. Okay. So let us find the particular time complexity of the function right now. Okay. So what you have seen here till now, that every time we are finding the middle element by 2 by making it by 2. Okay. By 2 by 2 by 2 every time we are doing. So what we are actually doing, we are dividing this n length of the array by 2. Okay. So what actually don't be confused with this part, like L plus H minus L by 2. Approximately this part we are taking and we are considering it as n. So just suppose you can take it as somewhere some other value like m also. I'm just considering it as n. So n by 2, n by 2. So it is going around n by 2 to the power k. Okay. So a time will come. We are trying to make this particular thing to 1, equally to 1. Okay. So we will do what? We will take log on both the sides. Okay. But before that, we will make L equal to 2 to the power k, and then we will take log n equal to 2 to the power, log of 2 to the power k, and log n equal to around k log 2, k equal to log n by log 2. So approximately what will happen? The time complexity, that is k, will become log n, and that is the actual time complexity. Okay. And if we take the space complexity, that will be also taking the around the same stack space, so that will be also log n. So both time and space complexity are log n. Okay. I hope so you enjoyed this particular video. If you enjoyed this, do let me know. If you faced any issue, you can comment out and let me know with the comments. I will try to explain that to you. Okay. Till then, take care. Bye bye. Jai Hind.